All right, so my name is Parks Easter. I'm with the XLF lab, the lead geotechnical engineer there, and I'm investigating the effects of fine particles on lunar regolith simulant angle of repose. Let's see. Yeah, this does not seem to work. Next slide, please. All right, so angle of repose is the steepest angle that a granular material can be piled before collapse. It generally reflects the internal friction and cohesion of an aggregate. So a more cohesive regolith is going to have a higher angle of repose. Next slide, please. This is extremely relevant for the lunar surface for a few different reasons. Angle of repose is a pretty simple measurement that can tell a lot about a regolith. So it's a measurement that astronauts can do on the lunar surface, just by piling some regolith. It's also a measurement that rovers and other equipment can pretty easily replicate. Previous slide, please. Thank you. It also, okay. It also, there are plans, as you can see from the images on the right, structures such as berms and other landing pads and habitats will rely on angle of repose to not collapse any regolith piles that are created. So, you don't want a rover traversing up a slope that is past the angle of repose, the known angle of repose of a regolith, or is likely to collapse. So to investigate this, a preliminary study focused on the effects of particle size distribution on the angle of repose of LHS-1 was conducted. These were split into two different experiments, one that consisted of size bins. So those are 100 micron size bins, as well as size ranges. So just increasing the overall range of the min and max of the regolith. This was attempting to determine if angle of repose is more affected by mean size or overall distribution. Overall distribution would affect things like density pretty greatly. So that's why that was done. You can see on the right some images of the different slopes. So, you can see where it maxes out at 100 microns, it's a pretty steep slope, whereas 500 to 600 microns is very, very much less steep. So the results of this preliminary study, well, first you can see how I split up the particle sizes. It goes 0 to 100, 100 to 200, up to 500 to 600. And then the particle size range group just continuously increases the upper limit, divided equally among, so like 0.01 to 300 microns would have 1/3 0 to 100, a third 200 to 100 to 200, and a third 200 to 300. You can see on these graphs that there are some pretty significant differences between these. So with the size bins, the larger particle size that we saw, when we were getting up to 500 to 600, there was a significant decrease in the angle of repose. So that was getting down from 40 degrees at 0 to 100 to 27 degrees from 500 to 600. That's a very clear trend downwards. The size range angle of repose had much less of a trend, and this was really surprising to see at first. So when you overlay them, you can see that even at the same exact mean particle size, if we look at 150 microns, for example, that's a pretty big difference, like 36 degrees to almost 40 degrees. And you can see that even with the mean particle size being the same, the particle size distribution trials remained pretty consistent in the 39 to 41 range, whereas the bin sizes decreased, the angle of repose decreased. So some findings from this was that mean particle size is not the only determining factor within angle of repose. Angle of repose is not hugely affected by the gradation of the aggregate either, which I was really surprised by. The major difference between these two simulants, so once we looked at these two and saw that they were different, in trying to figure out why that could be the case, we realized that the size range mixes maintained at least 15% less than 100 microns. So we went from low to high particle size range. So those low particles were always included. Those low sizes were always included in those regolith mixtures. So to investigate that further, an angle of repose study was conducted using the mixtures of coarse and fine simulant. So I took something that was pretty coarse, that would be a low angle of repose, so 300 to 400 micron LHS1, and I mixed it with LHS1D, which is really, really fine, behaves very differently. So I stepped that up from 5% fine to 10% fine to 15% fine and upwards, and got some really cool results. So you can see here that at 0% fines, the angle of repose is really low. Immediately after we add some fines to the mixture, it jumps up to about 35, and then to around 38. And then after 15% fines, you can see it really starts to taper off. So you get really a diminishing increase of angle of repose. So you can see here, the fines percent has the largest effect on the angle of repose below 15%. You can see at 5%, there's a 7.6% increase. At 10%, there's a 10% increase. After 10%, it goes 3.5 down to 0.1. This can really be shown by from 30% fines to 100% fines, there's only a 6.6% increase in angle of repose. So, at that point, what you're adding to it is really not changing it all that much. Just to verify that this wasn't caused by the specific mixture I was using of the 300, 400 microns, I did the exact same trial with much larger particles, so 2.8 to 4.5 millimeter. And you can see, even though the 2.8 to 4.5 millimeter mixture starts at a much lower angle of repose, very similar relationship happens. So 5%, it jumps really high. 10%, it jumps, again. And then it's kind of eerie, actually, how perfectly it matches it. After 15%, 20%, 30%, it really just doesn't go up all that much until you get to 100. So conclusions here are, above 15% fine content, there is a diminishing increase in the angle of repose. This relationship was consistent even with different coarse size ranges. And the implications for this are that, when we're on the lunar surface and we want to do ISRU, not have to bring components from Earth to the moon, and we're using the regolith, as a material, we can get a lot from a little bit of fines content. So, fines content within lunar regolith mixtures can actually be altered to achieve a desired angle of repose. Of course, the numbers will always be a little bit different on the moon with the lower gravity, but it's also possible that, maybe one day we'll be able to take the angle of repose of a site and estimate the fines content within that site. It's also really important from this study that size separation of lunar regolith will be super essential for in situ infrastructure development. We really need to be able to separate the coarse materials from the fine materials and actually do things with that. Figure out how to sieve in low gravity is going to be really important at a lunar base or any sort of infrastructure. So then I have my acknowledgements. Thank you, Dr. Britt, Julie Brissett, and Jared Longfox for all their help. Any questions?
We can have one question.
Hey, Charles from University of Maryland. How did you mix your samples? What was your method for mixing them?
Yes. So what we do, we have cement mixers. So we basically got the percentages that we needed of each size, 5% fines, 95% coarse. We cement mixed it for usually like up to an hour. And we just made sure it was really, really thoroughly mixed. And then we did our experiment.